I'm Ayers, and I'm working on formal proofs for mathematics. So this is when you have some proof, and then the dream is that in the future, one day, instead of writing a paper and then submitting it to archive or maybe a journal, you instead formalize your work and then submit it to an archive somewhere. What's going on?
Just press on the red dot.
Yeah, how do I? Okay, it's being sorted, gang. Okay, you're seeing my slides out of order, which is okay. So the idea is, okay, yeah, that's fine. So Lean is one of these tools that lets you start with formal logic right at the base and then build all of mathematics on top of this and then eventually talk about complex analysis or something like this. So this is a completely different approach to how mathematicians work, because when you're doing complex analysis or some numerical analysis problem, you really don't care about whether you're using set theory or type theory or something like that. All that matters is that you can exchange ideas in some way. So what these tools have to do is they have to be able to talk about formalization. They have to be able to prove everything formally, but then hide all of that logical stuff under some layer so you don't have to look at it all the time. Okay, so I'm going to talk about Lean, which is just one of these tools. There are others down here. I'm just picking on Lean because I like it and I'm using it a lot at the moment. Okay, so why should you care? So you need to automatically check that your proof is correct. So at the moment there are maybe 3 million papers on the archive, something like that. And then how many of those are maths? Maybe a few 100,000. Do you really believe all of them? No, but I also don't want to check them all either. So it would be great if all of these were somehow formalized, maybe in the future, and then you can just click a button and it will tell you, yes, this is true. That's kind of the dream. We've also got so you could kind of do the job of peer review. You end up like going through these absolutely weird things which you think would be obvious but they're not. So something like even proving that 0 is less than 1 for real numbers. Like in order to do that, you need to know that real numbers are a completion of Cauchy sequences, okay? And every rational injects into the reals, every natural injects into the rationals. So you have this big chain of inclusions, and then you have to show that each of these inclusions preserves ordering. And then eventually you can prove that 1 is greater than 0 for real numbers. But even things like that become really weird, and the things it gets held up on are kind of strange. And then also, I also want to talk about, this isn't just a mathematical problem, this is also a computer programming problem. So if you can prove that your piece of software is guaranteed to always do what the specification says it can do, that gives you a much harder guarantee of correctness than just doing unit tests. So there's actually a company doing this. I didn't write it on the slide, but there's a company called Asynchronous Integration, and what they do is they take documents which kind of explain how trading exchanges should work, stock exchanges should work, and they've formalized this, and then they use the automated reasoning techniques to find edge cases in these trading things. So there might be, like, if I trade and then immediately trade somewhere else, it will cause this flag to be switched, and then this means that I get money for free or something. And they're able to find all of these in a way that unit testing can't. So this actually does have loads and loads of applications in the real world. Also, lots of hardware is verified these days. Okay, so let me just talk about how Lean works. So Lean doesn't use set theory, it uses inductive types. So I think everyone kind of has an intuitive feel for what an inductive type is. So this natural is the classic one. So I have 0, 0 is a natural number, and the successor of a natural number is a natural number. That makes sense. And then you have a thing called an induction principle. So if you have that this property is true for 0, and if it's true for n, it's true for n plus 1, then you have it's true for all natural numbers. So that's kind of like, so the idea of inductive type theory is that you can encode any piece of mathematics in terms of these inductive types. So these should be, they should be familiar if you've done any functional programming, but hopefully you can kind of see how this maps to how you define induction on natural numbers. Okay, but you can also do some quite wacky things, like you can define or and so on in terms of this. So A or B is defined as the inductive thing where if I have A, then I have A or B, and if I have B, then I have A or B. So I can represent this as an inductive type. I can represent whether something is decidable. So is this proposition decidable? And then it returns one of these two things. And then the big one is equality. And it's not obvious at all that equality would work as an inductive type, but you can actually get everything to fit within this framework. So that's kind of why it's appealing. It's an appealing foundation to formalize things. Okay. Okay. So yeah. So what I'm going to talk about now is I'm going to try a demo, and I set it off just before I came up, and hopefully it's compiled all of mathematics up to complex analysis by the time I switch over to the demo. And so what I want to talk about now is how you do continuous structures in these formal systems, because that's the theme of the talk. And the answer is it's really weird, because you're no longer just talking to other humans. You have to get this logical system to understand what's going on, and yet it all has to compile down to inductive types at the end of the day. Okay, so the way they do it in Lean is they have these things called filters. So has anyone heard of filters before? We've got a few. That's great. Okay, so what a filter is, it's just super abstract. So it's you have some carrier set X, and then you have a family of subsets on X. X is in the filter, and any superset of something in the filter is in the filter, and the intersection of two things in a filter is in a filter. Okay, so why should we care about this? Because it means that you can talk about lots of different limiting processes as being examples of filters. So for instance, if we have a point in a topological space X, we can talk about the filter of neighborhoods of X. So we take any set at all. This doesn't have to be open. It can have like weird blobs. It can have closed bits. This is just a set of points, and as long as it contains an open neighborhood of X, then this is in the filter. Okay, and then so you take all of the sets with this property that they contain an open neighborhood of X, and then this lets you talk about it lets you talk about what happens as I get closer and closer to X, because you can talk about taking an element of this filter. That's kind of the idea. And then we can define tends to using this notation. So we kind of take the pre-image of f on some u, and if that's in the filter, then u is in this kind of f of a filter, and then we can talk about limits like this. Which time have I got? Okay, so now that's how limits work. So I'm going to go over to the demo. Please be done. Okay, I think it's done. Yay. So if it's orange like this, it means it's still compiling. So in order to get to complex numbers, of course, you need natural numbers, rational numbers. You need to prove things about fields. You need to prove things about Cauchy completions of rational numbers. And then you need to prove that you have complex numbers. You need infinite sums. So it's doing a lot to get to this stage. So hopefully, there we go. Yes. Okay. So I thought I'd just bring up a proof that I found in the wild, in the Lean library, to show you guys. Just to show, this is kind of, so the idea is, I'm just trying to show you that there's this other way of doing maths out there, and it's very, very different to how mathematicians do maths. So what are we looking at here? So I think I'll focus on this lemma, which I didn't write. It was written by this guy who writes code for Lean. And so what do we do? So we have tends to of the exponential, neighborhoods of 0 goes to the neighborhoods of 1. So this is saying x, as I let x tend to 0, exp of x tends to 1. Okay, and this kind of seems obvious to us, but you really have to spell this kind of stuff out for Lean, because, for instance, if I write exp of x is equal to sum of that r equals 0 to, well, that should be infinity. Okay, I've got to get this right now. Oh, fuck. factorial x to the r. Have I remembered exponential right? I think that's right. What does that mean? What does the infinity mean? What does an infinite sum mean? All of these things need to be spelled out in excruciating detail to lean, which is why you end up with things like this. Okay, but what I want to show you is that there is an attempt to make it look like a proof that you might find in a textbook. So here we have this lemma. I can hover over the lemma and it tells me what the type signature of the lemma is, and you can see that it's saying, okay, if f makes a tend to b, then I can also use this epsilon delta argument to prove that. So we're going to, and then down below we have the epsilon delta argument. So assume we have an epsilon. This is a proof that epsilon is greater than 0. Then we'll let delta be the minimum of epsilon over 2 and 1. Then we have delta is greater than 0 because of all this stuff. So we have things like norm num. So let's look at what norm num is proving. It's proving that 0 is less than 2. So that this is like a big deal for a computer to try and prove that. So we have a computer program which does it, and then so on. And so so we need, for all complex numbers, the distance between x and 0 is less than delta. The distance between e of x and 1 is less than epsilon. You can kind of so I'm not claiming that you should be able to read this straight off the bat, but hopefully you can see how it's starting to get some of the flavors that you might see in a textbook. And the same kind of notions are being talked about here. Okay, and then I think I'll stop now in the interest of time, but thank you very much.
Right, thank you, Ed. I never thought I would hear a talk with the construction of natural numbers and financial arbitrage together.
Yeah.
But, any questions? Right. Any
Right.
to, I guess you place.
So, in all of these formal verification systems, if you start from scratch, there's obviously a problem of combinatorial explosion. So,
Yeah.
is there some sort of a reuse of proofs that already exist, or a library of proofs
Yeah.
that you would have pre-compiled?
Yes. So this thing is called mathlib, and you can get so if you were writing a new mathematical library, you'd get a pre-compiled version of mathlib and run it. And then do your proofs on top of it. Whereas here I'm actually in mathlib, so it has to do all the calculations itself.
Second question is that how does it deal with inequalities? Because that's one of the things that we work with finite precision arithmetic at some point if you don't do things numerically on a computer. So is there anything that can actually deal with bounds and
Yeah. So you can do inequalities in lean. So let's there's one here, for instance. So how they basically work is you have your type. So for instance, natural numbers, and then you define inductively what less than means on natural numbers. So you say the successor of x is greater than x, and then I think there's also an induction principle here, which I can't remember off the top of my head, which lets you define less than everywhere. And you can also prove things like less than is decidable for the natural numbers, and then there are tricks and techniques to like lift the less than to rationals and reals as well. So whether or not real less than ordering on reals is decidable, I'm not sure if that's. I guess it's true if it's a Cauchy sequence. If all reals are Cauchy sequences, I think it's decidable. Anyway, yeah, so there are lots and lots of caveats, and I think this is probably, maybe in like the next 50 years, that these tools will be good enough that you can use them to do research level mathematics of them, I'd say. So there's still lots of problems to be solved in this area.
Is there any relation between this and non-standard analysis?
So you can also formalize non-standard analysis in these tools. So I think Isabel, which was made here and in Edinburgh, they have a non-standard analysis library. So and it uses ultra filters and so on to make the little dx element. So I'd say whether or not that's easier to use than this epsilon delta method of doing things, I wouldn't be able to say. But you can definitely do non-standard analysis with these tools. Yeah.
there are no more questions, then let's thank Ed and all the speakers.
Thank you.